it's day two, and topic two is Kolmogorov Axioms. So let's begin. Yeah, probability is just a function that maps events, and Kolmogorov gave the minimal rules to this function, just like it have to obey to be internally consistent. Okay, so everything in probability theory, every theorem, every distribution is built on exactly three axioms. So think of it like law of physics for probability. Okay. So what are these axioms for? Hmm, hmm. Like our probability measures, like probability range would be in 0 to 1. Okay. So this is the thing. Now let's see the measures. First is like there are three axioms of Kolmogorov axioms. First axiom is non-negativity, means the probability cannot be negative, and the second axiom is normalization, means probability of the sample space is equals to one, means something must happen. The total probability of entire sample space will be one. Now the third axiom is countable additivity, and we call it as sigma additivity also, and this is the formula how we denote it, and what it means is like if E1, E2 and E3 and many events are mutually exclusive. What are mutually exclusive? They have nothing common in them. So these events which are mutually exclusive, um, their probability of union, means probability of a union of these mutually exclusive events will be equal to sum of their individual probability. Okay, they the infinity here is a very important. It's finite additivity alone. Like additivity is alone too weak for limit theorems. So what it means, simple in simple language, E1 union E2 union E3 is will be equal to E1, probability of E1 plus probability of E2 plus probability of E3 when this E1, E2, E3 are mutually exclusive. I think I was able to make you understand this thing. Then next thing is like everything else derived from these, like these axioms are the main formula. Like we can say these are laws of physics only, like laws of probability. Okay, so no, no, I just said something wrong. Just remove it. Hmm. The foundation rules and what they prevent. Like this is axiom one, and probability cannot be negative. It can be zero, but it cannot be negative. Then axiom two, it was simply that it should be equal to one. The sample space probability should be equal to one, and countable additivity. It was just a conclusion slide. Next is like every other rule, everything else which is probability is derived from it. Like there is one complement rule which is here shown. You can complement. I guess I told you about in the previous video. Then comes impossibility, which is like probability of null event is equals to zero. Then there's monotonicity, simple meaning that if even is subset or equal to E2, then probability of E1 to occur is like less than and equal to probability of E2. This is being derived from axiom 3. Okay, like these like inclusion, exclusion, and bounds. These all things are derived from this axioms only. Now let's move forward. These are just some more rules like complement rule. Means E union E complement will be equal to sample space, and E intersection E complement will be equal to null event. Okay, easy to understand these things. Now apply axiom 3 like probability of sample space is equals to probability of E plus probability of E complement. This we just named it as Fires, like it is named as Fires law of summation, and there is one more law like Fires law of certainty, which is like applying axiom to one like P probability of E plus probability of E complement will be equal to 1. Okay, so yeah, we can move forward. Then there is just an example of cards, you can see it. Next is resolving overlapping events with inclusion and exclusion. Exclusion. Okay. So this is just the answer of previous question. Like in this card, 52 total outcomes will be there, and the probability of each card to happen is like 1 by 52. Each card to occurs is 1 by 52. Okay, so card of heart will be there are total 13 cards of heart. Okay, so for this too you need to know how like card system is there. Every card, how many cards of hearts are there, spade are there, diamond are there, and you can solve this question. This is a simple thing. Next, we move to danger zones, like where we can make mistakes from our sides. Okay, there is finite versus countable additivity. Some probability-like functions satisfy finite additivity, but not countable additivity. Like Kolmogorov specifically required the infinite version. Without it, the law of large numbers and central limit theorem can't be proven. This central limit theorem will come in our forward videos. Okay. So axiom 3 requires mutually second thing which where we can make mistake is like axiom 3 requires mutually exclusivity. Like A union probability of A union B is equals to probability of A plus probability of B only when A intersection B is null event. Okay, I guess like you can understand it by writing on paper. So like students like we drop the condition and get wrong answers constantly. The general formula always needs minus P A intersection B correction. Okay, so remember it. Now, the third thing, like these axioms don't tell how to assign probabilities. They only constrain what any valid assignment must look like. Whether you use classical 1 by n frequentist or Bayesian probabilities is a like a separate philosophical question. So all these are compatible with the Kolmogorov axioms. Okay. So the next thing will be like probability of any event equals to zero does not mean that E is impossible. Remember it. That probability of E is equals to zero does not mean E is impossible. On continuous basis, like individual outcomes have probability zero but can still occur. Like probability of x is equals to zero point 0.5 is zero for a continuous random variable. This is like a trip, this like trips people up badly in topic, like which will come in future videos. Next thing is like, okay, so paradox of zero. Okay, this I already told you. You can see this slide. It's very important to remember. Next thing is like ultimate pair of axioms inside neural networks. Okay, so why we are studying this for ML? So we use this in loss functions, regularizes, and probability distribution in ML. Uh, like all these three implicitly rely on these axioms being satisfied. Okay, when you define a model output distribution example like softmax, you are constructing a valid probability by enforcing axioms. Okay, so this was all for this video. I hope you understood it and liked it. So if you find any kind of mistake, you can just tell me in comment sections. Thank you.